I asked you to watch this video to just give you some background of the physics that involved in actually working out how hot the planet is or should be. So just to summarize that quickly, so this is the energy balance model that we're going to use. So there's the energy flows in to the Earth from the sun, and then that energy either reflects back out to space or gets absorbed by the atmosphere or whatnot. And if we can kind of quantify these fluxes, we can basically try and balance them. So we make the assumption that if the planet's temperature is not changing, the fluxes into the system must equal the fluxes out. If that's not true, then the temperature would change. So I think in the video we went through a simple example of that where there was no atmosphere. And the physics required for that was kind of really this, which is basically the StefanBoltzmann relationship between the temperature of an object, kind of any object, and the amount of energy that that object radiates away. So kind of the underlying kind of simplest way of looking at this is the hotter something is, the more energy it radiates away. Okay, so hot things like this piece of metal that's just come out of a forge, not a foundry, a forge. That's hot and it's giving off lots of radiation. So that's one thing that's important with this. The other thing is that the wavelength of energy that's given off in the electromagnetic spectrum gets shorter the hotter something gets. So that's explained in this kind of diagram here. So with something that's very hot, like the sun, okay, so that's got a temperature of roughly 6,000 degrees Kelvin. So it gives out a lot of heat energy, and that is represented by the area under this this curve here. Now it gives out energy across a huge range of wavelengths, okay, from kind of like infrared to ultraviolet over here. But the peak energy that it gives out is at this kind of short wavelength here, whereas another object, so the Earth, which has got a much colder temperature of around 300 Kelvin, okay, so that's giving off less energy because of its temperature. Okay, so that's the area under this curve, and you can see that the wavelength that is giving off is longer. Okay, so the two things to remember here is the hot things give off lots of energy, and that's kind of codified by this relationship here. So the total radiation emitted, so the area under these graphs, is proportional to some constant, which is this, weird small number here, the StefanBoltzmann constant, times temperature to the power of 4. And that power of 4 means that the hotter something gets, it really starts giving out much more energy. Okay, so that's that. The next kind of important thing is that the sun, it's very hot, it's giving out lots of energy, it's very big, but it is a long way away. Okay, so the energy that we receive at the Earth, that's from the sun, is effectively spread out over an enormous sphere that's the radius, the distance between the Earth and the sun. Okay, so we're basically diluting the energy flux from the sun by spreading it out over a huge area. Okay, so we're basically spreading out the solar flux, which is this Q. S0 is the amount of solar radiation per unit area we actually get from the sun. So, and this R squared is the distance between the Earth and the sun. So we actually get a relatively small amount of energy from them compared to the power of the sun, which is, quite hot and powerful. And the next thing is that energy is not is basically spread out over the surface of the sun, surface of the Earth. So the amount of energy we get from the sun is that which is intercepted by the Earth. So that's effectively the area of the Earth's shadow. In this case, A is the radius of the Earth, because we've already used R for the radius of the Earth's orbit. And that energy is spread out over the surface of the sphere. Okay, so there's a relationship between the surface area of a sphere and a circle, and that is where this divide by 4 comes in. So we're spreading out that area over 4 times the surface of the shadow, which is the surface of the sphere. So we actually get 340 something watts per square meter on the Earth's surface, and that's that number up there. Okay, so in the video we went through and basically described what the Earth's surface temperature would be if all that was happening was the energy was coming in, heating up the surface and radiating off back out in space, or just being reflected off the surface or clouds. Okay, and that reflectivity we call albedo, just the shininess of the Earth's surface, and it also includes how cloudy the planet is, because clouds also reflect the shortwave radiation coming in. So different parts of the Earth, like trees, are quite a low albedo because they're quite dark, whereas things like ice sheets or deserts might have quite a high albedo because they're quite, shiny. So this is the model that was in the video. So we were basically balancing energy that came in with the energy that came out of the Earth, either by reflection or emission because of the Earth having a temperature. Okay, and that was explained with these relations. That's the energy coming in. The amount reflected is the amount coming in times how reflective the planet is. So the amount absorbed is equal to kind of 1 minus how much is reflected. Okay, so we just balance these terms and we get an equation like this, which we can solve to give us what we call the emission temperature. So this is the temperature of the planet if it didn't have an atmosphere. If the only things that matters were the energy coming in from the sun and how reflective the planet is. Okay, so that's what we did in the little video. So this is a map of albedo. So different parts of the Earth are different shininesses, but we can average them all together and get a value of about 0.3. And that gave us, we plug those numbers into these equations, and we get a temperature of about minus 18 degrees Celsius, which we know is wrong. Okay, because it is a lot warmer than that on average. Maybe not in Scotland in winter, but on average the planet is not frozen. So the average is about 15, according to NASA, which are kind of trustable. So we've got to make our model a little bit more complex. We've got to add some things in, right, to that model. So we've basically already included this reflectivity term, and we've balanced fluxes at the top of the atmosphere. So what we're going to do now is consider actually what happens with the atmosphere. Okay? So before we were assuming that all of the energy from the Earth's surface, that just radiated straight out into space. Okay? But that's not true. Some of it gets intercepted by the atmosphere. So this is, I guess, the top. The solid lines are the theoretical kind of amount of radiation and wavelength of radiation that should be given off by the sun in red, okay? And then the Earth, for different temperatures of the Earth, in blue. Now, on the bottom here, we've got various components of the atmosphere, so things like nitrogen, oxygen, carbon dioxide, water vapor. So these are things in the atmosphere, and they absorb different wavelengths of light, or different wavelengths of electromagnetic radiation, as that radiation basically kind of starts to vibrate molecules. So you can see water vapor absorbs almost all of the radiation that tries to go through it in very long wavelengths, not so much in the short wavelengths, but there are kind of little peaks here and there in that short wavelength that do correspond to kind of individual bonds that are being shaken about and absorbing energy. So you can see that the actual shortwave radiation that reaches the Earth's surface from the sun, some of it is missing. Some of it's actually been absorbed by the atmosphere. Now, we're going to ignore that because it's not really, it's not a very big component of the overall radiation. If we're doing this kind of properly, we'd have to take that into account. But if we start to look over in the radiation that's being emitted from the Earth, because it's hot, this long-wave radiation, we've got much more absorbing kind of molecules in the atmosphere. So water and carbon dioxide and methane, they basically all add up and mean that a lot of this radiation that's trying to get out is absorbed by the atmosphere. Okay, so we can kind of start to build that into our model now. So what we've been considering before was these terms over on the left. So incoming solar radiation, some is reflected by the albedo. And then before, the Earth's surface warmed up and then radiated off out into space. But now some proportion, this epsilon, is being absorbed by the atmosphere. Okay, so if the atmosphere was completely transparent, that would be 0, and that term would equal this term, and that would be the same model as we started with. But as we absorb more and more of that outgoing radiation, this epsilon term gets larger and larger and larger, and means that some portion of this radiation from here is actually absorbed by the atmosphere. And if energy is absorbed by the atmosphere, that will cause it to heat up and have a temperature. And if it has a temperature, it will radiate heat away, okay? Proportional to the StefanBoltzmann constant times the temperature to the power of 4, okay? Okay? Then this emissivity term, this epsilon, comes in, and again, because it turns out that the amount of energy that a substance like the atmosphere would absorb compared to like absorbing 100% is also very close to the amount that it kind of emits as a fraction of the theoretical amount due to its temperature. So I guess only ideal kind of objects like the sun are so-called black bodies, where they emit the amount of energy that they're supposed to based on their temperature, whereas objects like the atmosphere, some of the temperature that they have doesn't result in them emitting all of the energy they should. So that's bound up in this term epsilon here. But that's a detail which is less important, but you can basically just think of these things as the same thing, the effectiveness of the atmosphere as of absorbing or emitting radiation. So what we can do is we can basically start to balance these terms at the top and bottom of the atmosphere now. Okay, so we're basically trying to balance the fluxes in and the fluxes out at two different places in the atmosphere. Okay, between the Earth's surface and the atmosphere, and between basically the Earth and space. So we've already done that for one side. We can do it at the other side as well. So we're basically at the top of the atmosphere, we're balancing these two terms, the one down minus the one up, plus, well, I guess minus the ones up and up. Okay, so we just balance those terms. There they are. Okay, so that should look familiar from before, and then we're just adding on this side this term. So basically, this should equal that, and that's what that equation there says. You've got another one at the ground, okay, which is the same thing on this side, okay, except we now have got this term here coming down, this term going up. Now, not going to go through all this now because that's a crazy amount of maths, but it's all gone through on Learn, and so you can, if you want to, solve those equations to show that we can come up with this equation for the Earth's surface temperature. There are some more maths of me kind of working it through. I used like a pencil and stuff. It's all really good. But the important thing is this equation here. Okay? So let's just look at that equation and see what is in it. Okay? So we've got the temperature of the surface of the Earth. Okay? And that can be described by the power of the sun, that S0, that's the amount of solar radiation we're receiving, okay, times this thing here with alpha in it, and alpha is the albedo, so that's how shiny the planet is, divided by 2, 2 is a constant, times the StefanBoltzmann constant, which is a constant, times this thing here, 2 minus epsilon, where epsilon is the absorptivity of the atmosphere, or emissivity of the atmosphere, or whatever you call it. So this means that the temperature of the planet in this model depends only on 3 variables. We can change the power of the sun, we can change the shininess of the planet, or we can change the absorptivity of the atmosphere. Okay? Those are the only things that kind of matter. Okay, so if we actually get a measure of how absorptive the atmosphere is, so the atmosphere actually absorbs quite a lot of the radiation that's trying to get through it, around 80%. We plug those numbers into our equation, and we get a temperature of the surface of the Earth of around 290 Kelvin. And that is quite close to the actual temperature of the planet. So our model is now doing quite well just by inserting a simple atmosphere. So I guess the important things for you to know are basically, I guess the model in the middle is less important. The one at the top is an important equation. I'll pause for 20 seconds to allow you to write that down. And then to know what these things are. So S0 is the solar flux, the amount of radiation received at the Earth's surface. Alpha is the albedo, the reflectivity of the planet. That doesn't have any units. Neither does epsilon, which is the absorptivity. And StefanBoltzmann constant has crazy units, and that's just a constant. Okay, so that's stuff you're going to have to know. So let's look at the relevance of this. So this is an example of just looking back through kind of all of Earth's history from now to the formation of the Earth 4.567 billion years ago. And throughout that time, the sun we think, has been becoming more and more powerful. Okay? As the star has evolved, okay, and become effectively more dense, as it's producing more helium through hydrogen burning, that increase in density has increased the efficiency of the nuclear reactions that are going on in the sun, meaning that over time the power of the sun has become more powerful. Okay? So if we look at what that means in terms of the Earth temperature, so this is what we would get if we used this model up here. If there was no atmosphere, okay, if there's no atmosphere, epsilon is effectively 0, okay, because it's absorbing no radiation. So the temperature of the surface is effectively the same as the emission temperature, because if we set that to 0, that just becomes 4 at the bottom here. Okay? So I guess first of all, we've already made the observation that means that in the modern we have a below 0 average temperature, which is no, that's not happened. And if we go back in time, it's got even colder. So this is not really consistent with our observations of the geological record and the history and evolution of life. Okay? Okay, this cannot have been true. We can't have only just got an atmosphere. Okay, kind of slightly ridiculous, right? So we could see what this would look like if we, oh no, if we, what? Yeah, okay, that's right. So if we've added in greenhouse gases, we've added in absorptive atmosphere, okay, so now we get our model up here, which gives us a nice warm temperature of the Earth. But actually, if we go back in time, this model, okay, if we keep all of these terms constant, still predicts that the planet was frozen up until about 1 billion years ago. Okay? Now, maybe that's the reason why we didn't have complex life on Earth. Okay? But we've got quite a lot of evidence that suggests that the planet was not frozen from looking at rocks from deposited in that period. So something must be different. Okay? So one of the things we think is that actually this emissivity term has changed quite substantially through time. So the atmosphere back here was like more greenhouse gassy. Okay, there were more gases in the atmosphere that absorbed the Earth's radiation, meaning it would warm the planet up here. Okay? So this is kind of what we're going to be doing for a large part of the course of the next few lectures, is basically looking at records of past climate change, okay, changes in temperature and other aspects of climate, and trying to explain them by looking at what has changed in the Earth system to cause those climate changes. Okay. So before we crack on and do that, there's some kind of terminology which you guys need to be familiar with. So firstly, a climate forcing is something that is going to be responsible for changing the climate. Okay? Now, so that means that it's probably going to be a change in one of these parameters here. Okay? Now, the response, climate response, is how much the climate changes for a given forcing. And that can be explained as a climate sensitivity. So, you know, how many degrees warming do we get per watts per meter forcing change. Another aspect of the Earth system is that sometimes these changes don't happen instantly. So the model that I've just shown has no concept of time. Okay? But in the real Earth, if you change something, okay, it might take a while for the Earth to heat up to that new temperature. Okay? There might be other things in the Earth system which require time for the planet to adjust to its new equilibrium. So this is what we call a climate response time. And then the last term is probably the most confusing for you guys, this idea of climate feedbacks. So a climate feedbacks is something very similar to a climate forcing. It's something that causes the climate to change. But the important difference is that a climate feedback, that initial change that causes the climate to change, was caused by a climate change. Okay? Whereas a climate forcing is independent of the state of the climate at the time. Now, some things, like atmospheric CO2, that can be a forcing and a feedback depending on what causes the initial change. So, for example, if we suddenly decide to burn lots of fossil fuels. Right? It doesn't matter what the climate is doing, that's our decision. We are independent of the climate, so we're burning lots of fossil fuels. So that would be a climate forcing. Okay? But you can also have, or if loads of volcanoes go off, right? The volcanoes don't know about the climate. Well, they kind of do, but let's ignore that for a bit. Right? So basically a sudden injection of CO2 into the atmosphere causes climate warming, not really dependent on climate. That's a forcing. Whereas there are feedbacks in the climate system, and we'll come onto these in future lectures, where the amount of CO2 in the atmosphere might depend on the temperature of the Earth. So if it warms up, CO2 is a gas that's less soluble in warm water. So if you warm the planet, CO2 will not want to be dissolved in the ocean, it will exsolve out, and the atmospheric CO2 concentration will increase. So you'll have an initial warming which will cause a change in CO2 in the atmosphere, which then causes a further change in climate warming. So in that case, that's a positive feedback. Now in this case, the positive and negative, this doesn't mean anything to do with how good it is for the planet or how good it is for us or the economy or whatever. It's just what is the final change kind of with respect to the initial change. So if you have an initial warming, that might change CO2 in some way and then cause more warming. So that's multiplied the initial change. That's a positive feedback. But we'll also see examples of negative feedbacks where you might warm the planet, then something will change, okay, which will cause the planet to cool down and act against that initial change. So that's a negative feedback. Okay? So that's quite hard to get your head around. We'll go through more examples of this in future lectures. The other thing to think about is that in that model I've just showed at the beginning, that described the temperature of the Earth or the Earth's climate as a single number, as an average temperature. Okay? So that's not really an adequate description of climate. So climate is lots of things. It's not just the average. So you can see this is a map or like a little movie map of the Earth's surface temperature. So one thing is you can see that there's a spatial pattern. Okay? So it's warmer in the tropics. Okay? It's colder in the polar regions. It's kind of maybe colder over land than at the ocean at any one latitude. So there's a spatial pattern, but there's also variability throughout the year. Okay, so there's seasonality. So sometimes it's cold, sometimes it's hot, depending on what time of year it is. So that variability, and that spatial variability and temporal variability, also are what climate is. Okay, so climate can be thought of the average of weather, but the average of weather you can't just describe the average of weather as just a single average temperature or a single average precipitation. You have to know something about what the average variability is. So to investigate this variability, we need to know something about the system. We need to know about how the atmosphere works, okay, and how the ocean works, because these are the two things that can move around, okay, and they can store and change temperature and energy. So this is the atmosphere. So you can see that it's kind of at the bottom here, the top up here, and it has a different temperature at different places in the atmosphere. Okay? And you can actually see from this where the heat is being added. So you can see that it's warmer at the bottom, and that's because the atmosphere is heated mostly from below, from the radiation coming off the Earth. Okay? It's also heated at the top of the stratosphere, so this is heating from the incoming solar radiation. Okay? So the atmosphere has got lots and lots of temperature, lots of different temperatures. The thing that we were describing in our model was this temperature at the bottom of the atmosphere. Okay. The atmosphere is made up of lots of different gases. I, really don't care about you learning all of these. It's mostly made of nitrogen and oxygen. That's maybe something you should know. There's a lot of water vapor in the atmosphere, which is an important greenhouse gas. And there's some carbon dioxide in the atmosphere, which is an important greenhouse gas. There are other greenhouse gases, methane, nitrous oxide. Those are relevant, okay, but only on very short timescales. And we'll come on to those in the last part of the course. Okay. So in terms of the spatial variability, the tropics, okay, down here, were the warmest. And the simple reason for that is that the Earth is round. It's not rocket science. If you've got at the equator, the surface is pointing towards the sun, and at the poles, it's pointing kind of away from the sun. So the incoming solar radiation is spread out over a wider area. Okay? So that 341 watts per meter squared, that's an average over the whole planet. It's higher in the tropics, it's lower over the poles. So this leads to this, basically, this temperature gradient. So this is the amount of solar radiation that basically gets to the Earth's surface. And you can see that it is higher in the tropics and lower at the poles. You can also measure how much radiation is kind of given back to space. Okay? And because the tropics are warmer, okay, they're also giving off more heat back to space than the poles. But the important thing is, if we just kind of flick between that one and that one, you can see in this one, in the outgoing radiation, the variability is a lot less. And that's because the Earth's atmospheric circulation has spread out that heat. Okay? So the net radiation, we're getting radiation in the tropics. That energy is being moved around the Earth by atmospheric circulation and also ocean circulation, which is heating up the polar regions. Okay? And those regions are then giving out to space more energy than they give in. Okay? So this is a cross-section from north to south of that process. So the amount of energy received is this curve here. The amount that it's giving out is the top curve. So you can see that we're getting more energy in the tropics than in the polar region. So this means that there must be a transfer of heat, okay, from the equator to the poles. And this gradient in energy in between the equator and the polar regions is what drives all of our weather. All of the movement in the atmosphere is due to this flow of energy. Okay? And that flow of energy is not in a kind of a straight line because the Earth is rotating. This is kind of details which we covered in other courses if you're kind of interested. Meteorology, weather and climate, and oceanography, or things like that. But basically, in the equator, it gets hot because lots of heating there. That causes the air to rise, and we have these kind of large-scale circulations within the atmosphere that move this heat energy from the equator up to the poles. Okay? Those flows are basically deflected because the Earth is spinning, so we get the Coriolis force. Again, this is not really for this course, but it's basically what gives us all of our crazy atmospheric circulation. I guess that's the idealized wind patterns on a rotating sphere. Those wind patterns do get somewhat deflected by positions of large mountain chains. Okay? But basically, the wind is moving around lots of this energy to whatnot. Now, the ocean is kind of the same. The ocean receives more energy in the polar regions. So, in the tropics, okay, receives energy from the sun and also from the atmosphere. Okay, so the atmosphere heats the ocean as well because it's warm. So that is providing energy in the tropics, and that energy must move away to the polar regions. So the difference between the atmosphere and the ocean is that movement is really much more inhibited by the position of the continents. Okay, because if you've got, say, a mountain chain, the atmosphere can kind of flow over and around that, mostly around. Whereas the ocean doesn't flow over continents, fortunately, for us. Okay, so it's constrained to these ocean basins. So this is the Atlantic ocean basins. We're in Scotland up here. This is Newfoundland, Greenland. And you can see that it's actually, I guess, quite lumpy in ocean basins. There's lots of topography, or as oceanographers call it, bathymetry, for no reason. There's a big mountain chain going down the middle. So the ocean is really constrained in terms of how it can move around because it's held within ocean basins. And there are also ocean basins which we can't see because they're basically split up by submerged mountain chains. So although there's not a kind of an island at the surface here, we can still see this water over here is isolated from this water over here, all that kind of stuff. Okay? The other big difference is the atmosphere is heated from the bottom. Okay? The atmosphere is heated from the Earth's surface, having a temperature, and that radiation trying to escape upwards. Which means that if you heat something from the bottom, okay, like if you were to boil some water in a pan, you'd get quite vigorous circulation, okay? Because that water gets less dense, rises up, bubbles over, all that kind of stuff. The ocean, on the other hand, is heated from the top. Almost all of the energy that goes into the ocean is from either heating from the sun or heating from the atmosphere. A tiny fraction is from geothermal heating at the bottom. And this means that you don't heat up the water very efficiently, because if you heat up the surface of the ocean, it gets buoyant, because it expands, it gets less dense, and it stays at the top. That means that it isolates it from the bottom. And if you do not try this, right? But if you were to try and boil water in a pan under the grill, okay, it will not boil. Okay, it will heat up at the top. That bit of water will slowly evaporate, okay, until you've evaporated all of the water right down to the last little bit of drop, and that might boil as you've heated up the pan with the grill. It is massively energy inefficient to heat up water under the grill, so don't do that. Yeah. Okay, it's kind of maybe okay to do it in Scotland because we get lots of our energy from wind power, but yeah, don't try that experiment, or do, you know, whatever. So this is the effect, the results of this heating from above in the ocean. So we've got this is a profile down into the ocean. So the surface ocean at 0 kilometers. The ocean is really deep, by the way. It's like 5 kilometers on average deep. Actually, no, it's about 4 kilometers on average deep. It goes down to 10 and a bit kilometers. It's a really big hole full of water. But it's only heated at the top, which means that we generate this layer of warm water that changes temperature quite a lot, but means that the bottom, the deep ocean, really does not get heated at all. And that leads to this basically having this layer at the top, which is kind of, because it's so much lighter than the water below it, it doesn't mix with it at all. So we have this buoyant surface layer, and because that's the bit at the top where, you know, the sunlight is, almost all of the life in the ocean is limited to this kind of like surface layer. Certainly all of the primary productivity, all of the things that are capturing carbon and growing, that happens in the surface ocean. So all of these processes that happen between the surface ocean and the atmosphere that exchange things like greenhouse gases and fluxes of carbon and nutrients, all that kind of stuff we'll come on to later. It's really important to realize that you're basically dealing with two separate bodies of water. The surface ocean and the deep ocean can be thought of being entirely separate things. But just like the atmosphere, they both move around and can transport heat and nutrients and all kinds of carbon, lovely things that live in the ocean. But that movement is very much restricted by the positions of the continents. And that has a big effect on how much heat transport you can move north and south, okay, where these continents actually are. Okay, this is an example of actually the sea surface height, I think, showing some of these flows of water. This is the loop current in the Gulf of Mexico, becoming the Gulf Stream. So you can see that this flow of water is actually quite complex. It's not at all kind of like those simple big arrows we saw in the thing before. But nonetheless, it's I guess you can kind of approximate these kind of large-scale circulations as kind of more generalized big red arrows. But it's not that simple. There's lots of complexity in the ocean, which makes it fun and exciting to study, which it is. So it's not just the surface ocean that's moving around, it's also the deep ocean. And the deep ocean, although it doesn't really get much heat from the atmosphere, is important because it is very big. Okay, the surface ocean is maybe only 100 meters thick, most places, whereas the deep ocean is many kilometers thick. So we can move around heat and other things that we can store dissolved in the water, like carbon dioxide. We can move things around the Earth system in deep ocean water. Okay, so what we're going to be looking at really for the rest of the course will be trying to understand some of these fluxes of stuff between different parts of the Earth system. And by stuff, I mean both heat. Okay, so these could be fluxes like what's the difference between the flux of energy coming in versus stuff that's reflected. We might be seeing changes in reflectivity through time if we maybe have grow ice sheets or cover more of the ocean with sea ice. That's replacing something that's got a very low albedo with something that's got a very high albedo. So these fluxes then of reflected radiation will change. Okay? We could be looking at changes in fluxes not just of heat, but of some of these, I guess, gases which can absorb long-wave radiation in the atmosphere. Okay, so CO2, so we might be looking at a change in the flux of how many volcanoes there are. Okay, so the amount of volcanoes that have been going kaboom on the planet has not been constant through time. It changes. So that might introduce more greenhouse gases into the atmosphere, which would increase the absorptivity, that epsilon term, and that would then increase the surface temperature of the planet. Okay, we might start to think about fluxes in between the ocean and the atmosphere. You know, can we store more heat in the ocean than in the atmosphere? That will cool the atmosphere. Or can we, in fact, store some of these climate-relevant gases? Can they be stored in this deep ocean down here rather than being allowed to interact with the atmosphere? There are all kinds of other kind of components of the Earth system that we're going to be looking at. And one of the important things is that these processes happen at different rates. Okay? So these changes in flux, so for instance, if we were to suddenly have something that made that there was more sea ice in the ocean, okay, that would instantaneously change the albedo. Okay, so that would cause a very quick drop in the Earth's temperature. Whereas if we did something that might change weathering, okay, so I'll ask you to watch a video before tomorrow, and next lecture will be on how weathering affects climate. Okay, so weathering is quite a slow process. It takes quite a long time to erode and chemically dissolve away a mountain. Okay, but that process removes carbon dioxide from the atmosphere. Okay, so so a change in weathering will also result in a change in temperature, but that change will happen much more slowly. Okay? And this is one of the really cool and interesting things about Earth sciences, is that we have records which operate or are recording how the Earth has behaved on all of these different timescales, which allows us to basically understand all of these different components to really get a good picture about how the Earth works. This is a horribly complicated diagram, but it I'm just trying to summarize what I've just said. Is there are a whole bunch of things that could change the Earth's kind of climate. These would be forcings. Okay, so things that are totally independent of climate. So a change in the sun's strength. We could actually change how far away the Earth is from the sun. That would change the temperature. Or we could change like the amount of volcanoes that are going off. Or we could like start burning fossil fuels for shits and giggles. All right? Now those things will cause a change in the climate system. Okay? But there are, I mean, all of these different parts of the climate system are interdependent on each other. Okay? And they are sometimes dependent on climate. So for example, this sea ice, okay, how much sea ice there is maybe a little bit, dependent on how cold it is. If the planet's very hot, not going to have so much sea ice. Okay, so there's going to be a feedback in between the amount of sea ice and the temperature changing the sea ice, and then the sea ice changing the temperature. These processes that might change the fluxes of carbon in between the atmosphere and the ocean, they might be dependent on, say, the temperature through the solubility of CO2, but also the biosphere. How active are phytoplankton in the ocean into capturing CO2 from the atmosphere? There might be climate dependencies in between vegetation and weathering, how the plants and bacteria interact with rocks and change kind of climate important gases. So there are lots of interactions between all of these individual processes, okay, which is what makes it a hard problem and therefore an interesting problem. Because if it was easy, I mean, there'd be no point doing it with that. So all of these interactions ultimately end up in kind of changes in different aspects of the state of the Earth system. And that can be changes in the temperature of the atmosphere or the amount of precipitation. But it can also feed back into ultimately changing things like, patterns of vegetation, or, changes in ocean circulation, all kinds of cool and interesting things. So I've mentioned that these things happen at different times, at different rates. So things like changes to the atmosphere, they can be relatively fast, okay, because the atmosphere has got a relatively low heat capacity compared to the Earth, and it can move around quite quickly. The ocean can take, quite a long time to change its temperature. It's quite hard to slow down an ocean current because it's, got quite a lot of momentum and lots of heat in it. But there are also really, really long-term changes, which, say, for instance, like melting away an ice sheet, that might take thousands of years. Changing deep ocean circulation, also thousands of years, or weathering may even take millions of years. So what we're going to be doing for the rest of the course, course that's this part, that is part 2, although it says part 3, but it's part 2, is we're going to be looking at periods of change in the Earth system that have happened on different timescales. So we're going to start off looking at changes that have happened over millions of years and how the climate has changed and what has driven those changes, what forcings and what feedbacks have operated over those timescales. And we're going to move forward into kind of through kind of shorter and shorter timescales, looking at different rates, different processes that occur at different rates that have had quite important effects on basically determining the habitability of the planet. Some of these changes are linked to changes in kind of, the evolution of life on Earth. Okay, so there's the idea that some of the, we have rapid changes in climates that might link to having, give rise to changes in rates of evolution, which you might have done with Steve. Yeah. So that's really the end of today's sermon. The important things to remember really are this equation here. So we can describe the temperature of the Earth's surface by a really simple relationship that only has 3 kind of important variables. The temperature of the power of the sun, or basically how much solar radiation we're receiving at Earth, because we could change the distance as well. The reflectivity of the planet, how much the albedo is, or how shiny the planet is, and the emissivity or absorptivity of the atmosphere. So how much of the atmosphere basically acts as a black body? How much does it act as a perfect absorber? The other points on here is that, so climate is not just the answer to this equation. Okay, it's much more complex, and it's much more. You have to consider the variability in terms of time and in terms of space as well. Okay. There are other things on here which I'm sure you can read. The PowerPoint is uploaded already to Learn, and hopefully this red light means that it's recorded. So there's that to do. I think the last thing is, so if you go to, you see it says part 2 here, which, there we go. So if you go to Learn, you head to kind of like course content, I think it is, and then part 2, and then they all have thingies. So if you click on that, there's a place for you to go and watch the video, which is amazing. I'll just make sure that it is there. So if you go to part 2, global climate and thingy change, the next lecture will be lecture 2. And watch this video. Watch it. It'll be fun. There you go. Not sure why that's not making any noise. Okay, if you've not signed in, if you've not signed the thingy, there's a sign-in sheet. Who's got a sign-in sheet? Anybody? Sign-in sheet? Nobody? In a folder all the way at the back. You just sign that. So it's not that I want to track that you're here. I'm just using it to check if people are repeatedly not turning up. There might be some kind of reason for that, which we might want to know about and see if everything's okay. So we're not kind of anyway.